This lesson is for the second day in solving nonlinear systems. Just as a reminder, we're talking about things that aren't necessarily lines and where they intersect. Perhaps there are multiple intersections, perhaps there's only one, maybe there aren't any. Today's first example asks us to solve the system by elimination. It looks a little bit difficult because we have two parabolas. We have x squareds and x's and y's and constants. But the nice thing is that they're lined up right on top of one another, and if you notice the y's, we have a negative 2y and a positive 2y. So elimination seems like the best method. If we add these together right now, the y terms are going to drop out of our equation. So in step one, let's go through that process. Let's add these two together and see what we come up with. If we're going to solve, it's going to be better for us to have 0 on one side of the equation. So if we bring the 2 over to the left, we have 4x squared minus 4x plus 2. There's a lot of different ways to go about trying to solve this, but factoring isn't going to work. So I'm going to suggest that we use the quadratic formula. You've seen that before in Algebra 1, and we'll revisit it again soon. It's negative b plus or minus the square root of b squared minus 4ac divided by 2a. So we've got these coefficients color-coded here so that when we plug in negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a, we can see how that's going to work out. And in a moment, we're going to simplify that expression. For example, the very beginning here, the opposite of b, negative b, it was a negative 4 that we plugged in that becomes positive 4. Please don't fall into the trap of thinking that the first portion of the quadratic formula always has to be negative. It's the opposite of what b is. So doing a little bit of simplification, we get 4 on the outside, we get an 8 in the denominator. And under the radical is called the discriminant. We have negative 4 squared, that's a positive 16, and we're going to subtract 4 times 4 times 2. That's 16 times 2, that's 32. When we look a little bit more closely, just zero in on the radical. What's underneath the radical sign, the discriminant, reduces to negative 16. We now know that we can take the square roots of negatives dealing with complex numbers, but those give us imaginary solutions. We're trying to figure out where do these things intersect one another, and if under the radical is negative, if the discriminant is negative, then it means there's going to be no real solutions. In example 2, we're asked to solve the system by substitution. This seems like a little bit of an easier challenge for us because one of our equations translates into a parabola, negative x squared plus 4, and the other is a line, negative 4x plus 8. If we're going to do substitution and we have y equals on both, then it might make sense for us to substitute for y in the first equation. So on the left-hand side, remove the y and substitute it with negative 4x plus 8. Just like in the previous problem, it would be best if we work everything to one side of the equation and solve a trinomial. And I'm going to suggest we move it to the left. It's going to make our negative x squared become positive minus 4x. And when we move the 4 to the left-hand side by subtracting, we result with 4 also. So now we have our trinomial, and we want to try to factor this thing. If it works, we can set ourselves up into two sets of parentheses, and I think it makes sense that we should have x and x at the front ends. And when I look at my signs here, I recognize that we want to multiply at the back end to get a positive 4. That means our signs need to be the same, and we want to add to get a negative 4. So since we want to multiply to get the same value and add to get negative, we're going to want to have negative and negative. We also want to multiply to get 4. That could be 4 and 1 or 2 and 2, and add to get 4. So our values will be 2 and 2. So now that we've factored, we want to be able to solve for x, and x is going to equal 2. Please note that since both of those sets of parentheses were x minus 2, we're only going to have one solution here, and that's going to be known as a double root. In step 5, we're trying to find the coordinates. We have our x value, but now if we substitute for x, we'll be able to figure out what y equals. So we have in our first equation, y equals negative x squared plus 4. We could put in a 2. In our second equation, we have negative 4x plus 8. We could again substitute in a 2. And for our first equation, order of operations, if we take 2 and square it, we get 4. There's a negative sign on the outside. The opposite of 4 plus 4 gives us 0. If we want to check for our second equation, negative 4 times 2 is negative 8. Negative 8 plus 8 also equals 0. So that's suggesting to us that 2, 0 is our point of intersection. Our third example, we're asked to solve a nonlinear system by substitution again. And our first equation is what's different here. X squared plus y squared equals 25. We haven't seen an equation like that since geometry. If you recall, that's a circle centered at the origin with a radius of 5. We also have y equals 4/3 x. That's a line going through the origin with a slope of 4/3. Do this line and circle intersect? We have to solve the system. We're asked to use substitution, and if you notice that the second equation has y equals, then we'll be in good position if we substitute for y in the first equation. So wherever we see y, we want to put in the 4/3 x, and we're going to try to, in step 2, rewrite the equation. We want to deal with that squaring business, and we also want to add. So when we square 4/3 x, we're going to get the x squared, but 4/3 times itself is going to give us 16/9. We want to add on the left-hand side, so I'd like to refer us back up to that first step. It's 1x squared, so if you can think of that as 1 over 1, we want to find a common denominator. So if we convert that to 9/9, I hope that makes sense. That now gives us the ability to add these two expressions on the left together. 9/9 and 16/9 should get us to 25/9. X squared equals 25. And our goal ultimately is to be able to say what x equals. So we've got to deal with the 25/9 and then the square. So let's get the 25/9 first. If we multiply by 9/25, the reciprocal, we're going to have to do it on both sides of the equation. We choose the reciprocal because when we multiply, it knocks out everything on the left so that we only have x squared. And when we do that on the right, the 25's cancel out, and we'll just be simply left with 9. So in step 4, we now have x squared equals 9, and we want to be able to get x by itself. So you know that we need to take the square root of both sides. When we do so, it gives us plus or minus 3. So if we have x equals plus or minus 3, we're now in position to solve for y. There's two options here. We have to consider both. If x equals 3, then y equals 4/3 times 3, and y should equal 4. Those 3's are going to cancel out. Y equals 4. If x equals negative 3, then y equals 4/3 times negative 3. The 3's cancel out, but we still want to hold on to the negative, so y can equal negative 4. Therefore, when we talk about the points of intersection, we have 3, 4, and we have negative 3, negative 4. Our circle and our line have 2 points of intersection. In example 4, we're also asked to solve by substitution. This time it tells us that a range in miles of a broadcast signal from a radio tower is bounded by a circle given by the equation x squared plus y squared equals 1620. So you can imagine that the origin is this tower, and the radio signals shoot out, forming a ring. A straight highway can be modeled by the equation y equals negative 1/3 x plus 30. So there's some road that's traveling through within this circle of radio space. For what lengths of the highway are cars able to receive the broadcast signal? So I know that you can see this picture on your page already. When we draw that, the radio tower is at the origin, and if we graph the line as well, we'll see that the red line intersects the black circle, and we have nice points of intersection, negative 1836 and 3618. So how long can we be driving on this road and still hear the radio signal? When are we within those boundaries? That distance is the distance formula. I'll encourage you to recall what that is. It's a souped up version of the Pythagorean theorem. And now we have to plug in our values for x1 and x2, y1 and y2. I'll let you write those out. Remember to be careful. It doesn't particularly matter which is the first and which is the second point. You can say negative 18 minus 36 or 36 minus negative 18. That order doesn't particularly matter, but please make sure that you're subtracting the x's and squaring and subtracting the y's and squaring. When we deal with the order of operations, we're subtracting a negative 18, so we're really adding. That's going to feel more like 54. When we subtract 18 minus 36, that's negative 18. When we square both of those, we get 2,916 and 324. And if we add those together, we get 3,240. We want to know what the distance is along the road. You're not going to see a road sign that says radical 3240 ever. We want to convert this into units that are going to make sense to us, and it's approximately 57 miles. The goal of this section is not really to graph our examples, but since we saw an illustration in the last one, I thought maybe it would be worthwhile to see these as well. Example 1, remember we had two parabolas and we tried to see where they intersected, and through our algebraic work we found that there was no solution. So when we graph our two parabolas, we see that they come close but they never actually touch. To solve a system, we want to find out where do things intersect, and these parabolas don't. In the second example, remember we came to a double root, we came to one particular answer even though one of our shapes was a parabola. That's because the parabola and the line intersect in only one point. You can see both shapes, and although it looks like they are extremely close over on that right-hand side, they actually only touch, they are tangent at 2, 0. The other points, if we zoomed in, we would see are getting closer and closer and closer, but they don't actually touch. And finally, in the third example, we had the circle and the line, and we found that there were 2 points of intersection. That's because that circle, centered at the origin with a radius of 5, is intersected by the line that goes through the origin and has a slope of 4/3. To rise 4 and run 3 means we would touch at 4, 3. To come down 3 and 4 to the left, we would also intersect at -3, -4. That should remind you of a 3, 4, 5 triangle, which also suggests that the radius of the circle is 5. You can see that from where it's intersecting the x and y axes, but also that purple radius going from the origin out to either point on the circle would also have to be 5 units long, and I hope you can see why that would be the case.